Okay, in this part of my introduction, this is the second part of my introduction, I'm going to start by looking at how we actually can assess the performance of a control system, i.e. how to look at system response and make a decision to see whether it's a good response or not. So we need some parameters to measure. Otherwise, we won't really have a definite answer to the question of good performance or bad performance. Okay, so we have some measurements there. This is one of this diagram here is one of the typical way of measuring system performance. Now, imagine you have a system and you want the system to behave in a certain way. So you say, right, I'm going to ask you to behave. In this case, I want your output to start from 0, goes to 1 in an instant, and keep that value there. Okay, so this is a 1. This is what I want the system to do. And I want the system to do that from 0 to 1 in an instant. And of course, system will have delays. It's like what you ask people, say, right, I want you to walk from here to the end of the corridor in a 0 second. Of course, that's not possible. Okay, it takes time to respond. So the system won't do exactly that. It will not jump from 0 to 1, but it will start to go there, towards there, but takes time. Sometimes it may get over a little bit, but sometimes it may not. So the time, but it doesn't necessarily get to what you want all the time. It may go over, but then comes down and then settles at a value. The difference between the value it finally settles down is called a steady state value. The difference between the steady state value and your target, that difference is known as the steady state error or steady state control error. Okay, so that's one of the parameters that we often use to measure the performance, to see how much it actually can achieve. The second parameter we tend to use is the rise time. The rise time is the time of the system response takes from 0, rises to 90% of the final value, not the input, the final value of the output. Okay, it's a time, that little time there. Okay, it's a time it takes from 0 until the 90% of the final value. That's known as the rise time. And of course, if you want a fast response, the rise time should be short. If rise time is increased, the response is slow. The third parameter is overshoot. It's amount of value it goes over the steady state value. Often we represent that in a percentage term. So it's that little bit there divided by the final value of the output, not input. Okay, so express that in terms of a percentage. That's third parameter. The fourth parameter is known as the settling time. It is the time for the system to take from 0 until it goes up and drops down and settles down to within 2% of the final value, and it won't go out of that 2% boundary anymore. Okay, so that's the time is known as the settling time. It's also a measure how stable system is. It doesn't go wobble. It doesn't go up and down anymore. Okay, so there are 4 parameters we tend to use to measure a system response, and we use a step input of 1 as our input. In practice, your input may not be always a step signal, but we use that as a design mechanism or design measure. Now, this control theory, it's called a PID control theory, is one of the typical controllers that we use for systems, or to control the systems. And then actually, perhaps 90 to 95% of industrial controls employ a controller like that. What we have here is to say, right, if I have a motor as my plant, that's object to control, I have an output, and I measure that, and I send that back to my comparator and compare with the input, which is my desired output. The difference, which is the control error, is fed into a controller. Now, when we use PID control for a control system like that, this block represents what the PID control does. Okay, so it does all the data processing and sends out a control action to say, right, this is what I want that plant to do. Okay, this output contains or may contain 3 different elements. The first element is called P control or P term. P stands for proportional. That means the output there, the output U is proportional to the control error, E. The proportional Kp, the value Kp here is a gain we select. It's how much you multiply to the control error. So if the error goes up, the control output also goes up. If error comes down, the control output goes down as well. And because it reacts instantly, anytime the error goes up, the control output goes up. Anytime control comes down, the control error goes down, and it is in a proportional relationship. So that's why it's called proportional term. Kp, remember here, is a gain we select as a control engineer, or we tune sometimes online. The second term of that controller is known as the integral term. Okay, so if you look at this term there in the middle of equation 2, it is the integration of the control error from time 0, I've not marked the 0 there, but it is 0 to control, go back, to the time of any time of your control with a control gain of Ki, okay? That again, this is a gain we tune, okay? It's called Ki or I term gain. And the output Ut of this part is proportional to the integration. Therefore, it is integration of the error that determines how much output is multiplied by Ki. The third term is known as the derivative or D term. Kd is a control gain. The third control gain or the D term gain we tune. And this term is proportional to the derivative of the output error, the control error. So therefore, the term is decided by how fast or how slow of the control error happens or occurs. So it actually measures the rate of change in control error. So in combination, all 3 terms together, we have P, I, and D control. Of course, we don't have to use all three terms at the same time, depending on your specific applications. Sometimes a P control alone might be enough. Sometimes you might want to combine that with a second term, the I term. Sometimes you may combine the P term with D term, or sometimes you might want all three at the same time. But it all depends on your applications, and you have at least you have three parameters to select. Okay, you can set them at 0, but which will make that term to disappear. But if you want to use that term, then you have to select decent values. Now there are ways of, or number of ways we can select these values. This is what we will need to discuss during the course of this module, how to actually design control gains and select the control structures. Now, over here, I have decided myself that I want to use a controller for a particular system. Now, never mind what that system is, it's not important. The important thing here is I want to illustrate the effect of three terms on the performance or on the output. Now, for this, on this slide, I have 4 diagrams for the system response, and I set the second and third term both to 0. So there's no integral control, there's no derivative control. The only term I have here is a P control, the proportional control, and I set the input to a step, a unit step from 0 to 1. And I choose different control values for Kp. So there's 20 on the top left, 50 top right, 200 bottom left, 500 bottom right. Now note that I have different scales for the y-axis. Okay, the x-axis is the same for all 4, so from 0 to 5 seconds. But for this first one, it starts from 0 to 0.7. So you can see there, although my input is 1, my output doesn't quite get to 1. Okay, it gets to just under 0.7. So the steady state error is actually more than 0.3. And the rise time, if I just look at around 90% of the output, the final output, I get around just under 0.5 seconds. Okay, and there's a little bit of overshoot, not too much. Not too much. There's a little bit of overshoot there, but not too much. The settling time is perhaps just 1 second around that point. Look at that. If I increase the control gain, the rise time is reduced from 0.5 to around maybe 0.2 something. The final value is now is above 0.8. Okay, so now the steady state error between the output and my input of 1 is less than 0.2. Now, but I can start to see some overshoot. So this value there divided by my final value give me an overshoot. Settling time is practically fairly similar because of this wobble. Okay, this goes up and down and then settles. Okay. Increase that gain even further from 50 to 200, we have this response. Now you can see the final value is above 0.9, it's perhaps about 0.95. So you can see the steady state error is reduced from over 0.3, less than 0.2, to perhaps around 0.05. The rise time is a lot quicker. It's probably 0.1, something like that. Takes that 0.1 second to go from 0 to 90% of the final output. Overshoot is a lot bigger. So this is around 1.3 compared with 0.95, so it's more than 30% of overshoot. And it goes up and down quite a bit and then settles down. So it doesn't really change the settling time that much. Perhaps it's actually a little bit worse. From 200 to 500, now you can hardly see any steady state error. The output is getting very, very close to 1. It's not quite 1. There's still a little bit of steady state error there. The rise time is even faster, but overshoot is more than 50%. And it takes quite several cycles to settle as well. So the system becomes more auxiliary. Okay, so just to summarize this diagram or this slide, if you increase, if there's no integral control, there's no derivative control, we are only relying on the first term, the P control. If we increase control gain from 20 to 50 to 200 to 500, this has an effect of reducing the steady state error, reducing the rise time, but it tends to increase the overshoot, and it doesn't help that much with the settling time because of this auxiliary response. Now, if I keep the proportional gain to a constant, and let's look at or examine how integral gain behave, what it does. Okay, so over there, my Kp, the first term, proportional term, the gain is set to 100. On the top left, my Ki term, I set the gain to 500. Now you can see there, in steady state, it goes to 1. So there's no steady state error anymore. This is the main reason why people use integral gain. It has an effect to try and eliminate, not reduce, eliminate the steady state error. But if you look at overshoot, there's quite a bit of overshoot. Okay, so it has effect of increased overshoot. But if you're not careful, you get the control gain too large. In this case, control gain is 1300. Now you see another oscillations. The sine waves, the amplitude of the sine waves gradually reduces, but it takes very, very long time. If you see the trend, if I run the system further, you can see it probably takes quite a while for that sine wave to die down. Okay, if I increase that a bit more, you can see the amplitude of the sine wave doesn't even reduce. It actually gets going on and on and on forever. If you start from there to the bottom left, if you increase the gain even more, then this sine wave gets worse and worse. Now this is a condition we call unstable. Okay, because the oscillation gets bigger, it gets out of control. It's something we want to avoid as control engineers. Okay, so in summary for this slide, the integral gain has the effect of eliminate the steady state error, but you need to be careful with stability, not to use that gain too much. It is possible for many systems that you only use these two terms with a properly tuning of proportional gain, integral gain to give you a good response time, no steady state error, controllable, reasonable overshoot, okay? And as the one you can see on there, it settles quite well as well. The rise time is not too bad. So, but sometimes if you do have problems with overshoot or stability, we tend to introduce the third term, the derivative term has an effect of helping with the stability or reducing the overshoot. So in this case, I fix the Kp value, the gain for the proportional term. I fixed the gain for the integral term. I'm only changing the third term, the derivative gain, from 2 to 5 to 10 to 20. You can see how the overshoot is reduced. So from there, just under 20%, to there, perhaps little over 5%, and to there, almost hardly any. Okay, but that's probably quite a good response. If you increase a bit further, then the settling time tends to increase a bit. The rise time is going to be okay, but the settling time, it takes a little bit of time to suppress that overshoot altogether. Okay. So here we have 3 different terms. And again, I need to emphasize, you don't have to use all 3 terms at the same time. Sometimes you may, sometimes you may not, depending on what your system is and what your control requirements are. Okay, so that's kind of controller. We just as a start for introduction. So, and this is just an example. Say, right, I'm quite happy with that response. I actually use all 3 terms, and that gives me a quite reasonable rise time. Now note that I changed the axis a little bit from 0 to 1. Not previous diagram is from 0 to 5. So the settling time now is 90% is there, is just over 0.1. A little bit overshoot, not too much. Steady state error is 0, and settling time is perhaps 1 to 1 second. It's quite a good response. But again, that's just for that particular system. I'm not even going to talk about what that system is, because I want to use this to explain the effect of 3 terms, not what the plant or what object you want to control is. Okay. Now finally, as part of my introduction, I want to talk about the design process, or the steps that we typically go through as a control engineer. If you get a job, say right from your company, say I want you to design control systems for that, these are the typical steps you need to go through. Okay, step number 1, we need to understand what the aims for control. Okay, what we want the plant to do, what are aims. Secondly, identify the variables to control, whether what we want to control. For example, if you drive a car, you want to control the speed, or you want to control the position, or you want to move the control the movement, that kind of stuff. So what kind of variables we want to control, which in turn determines what kind of measurements we need, what kind of feedback we want. And with all that, you write a specification called a design specification. Say, now I want that to behave in a certain way. What's the rise time? What's the settling time? What's the overshoot? What's the steady state error? That kind of stuff. Now, once you've done all that, then you need to understand your system better. Okay? And what actuators you need, what actions you need, whether you're going to use an electrical motor or use a hydronic pump, and what hardware you need or hardware you are given. Okay? So that's understand what you need. Sometimes you may need to change, say, right, this actuator is not good enough, or this motor is not fast enough, I need a more powerful motor. Or sometimes you may have a cost-cutting issue, say, right, where can I save money? I might say, well, for that set of requirements, I may not need that a powerful motor or powerful pump. I can do with a smaller one, therefore save some money. So sometimes you have to look into things like that, practical issues. So once you got all that, you need to understand your plant or the process, the object you want to control. And typically, we need to establish a model for it. And that's basically a mathematical representation of your plant. And your actuator, how you represent in a mathematical sense, and your sensors, everything put down on paper, basically, in equations. Okay, so that process we call modeling. We need to know the plant. It really doesn't matter. Sometimes people wonder, what system are we talking about? I'm a mechanical engineer. Or somebody would say, I'm a petroleum engineer. Or somebody might say, I'm an aeronautical engineer. It doesn't matter. It's for different plants, we need to derive a set of mathematical equations that represent the behavior or characteristic of that plant. Once you pass that stage, now you are dealing with a set of mathematical equations. Whether it's that mathematical equation represent a mechanical system or electrical system or petroleum plant, it doesn't really make a system. Doesn't really make much difference to control engineers because we are now dealing with that. This is really what we're going to do. For the most part of this module, we are looking at them as a set of mathematical equations. And then based on the knowledge of the plant in terms of mathematical equations, then we can decide how to design a controller and also how to fine-tune, analyze the performance. Sometimes we may have to go back to in an iteration to say, right, actually it doesn't do what I wanted to do, even though I done my best in the control design. You may need to go back and examine whether you have the right actuator, whether your modeling is done properly, or there are some errors in there, or you have to find the problems in the system. So sometimes you have this process may take several iterations until you get to the final value. So for remaining of this module, we're going to talk about the modeling part, how to actually convert or transfer a plant object for control into a set of mathematical equations in different formats. How to analyze the system behavior or characteristics of the system in a mathematical sense, and then how to design controllers and evaluate the performances. So that's really sort of introduction to this course. So from next time, we'll get on with the actual work. So I'll see you next time. Thank you.